For over a century, humanity has captured the world through an elaborate deception: the frame. The modern standard camera is an illusion. We snap 30 to 60 still images every single second, flashing them before our eyes to create a mere ghost of movement. But beneath this trick of light and mechanics, a vast emptiness exists. Between those captured frames, the machine sees absolutely nothing.
Standard cameras are blind. By relying on this archaic sequence of fixed intervals, we are drowning our processing systems in redundant data from static, unchanging backgrounds, all while remaining functionally blind to the high-speed vitality of the real world. A machine operating on frames is trapped in a strobe light, entirely missing the continuous, flowing reality that exists between the flashes. To truly unlock the next era of robotics and autonomy, the artificial eye must undergo a biological awakening. This demands event-based vision, a radical sensor architecture that abandons the frame entirely to perceive continuous motion at the scale of a single microsecond. It serves as the vital biological power revolution necessary to propel machine perception out of the industrial age.
The evolution begins with the silicon Retina.
The mechanical camera is a flawed industrial artifact. The biological masterpiece of efficiency found in the human retina operates on an entirely different paradigm. The human eye does not operate at a frame rate. Your retina only reports when it detects a change in the scene. If nothing moves, the neurons remain silent. This brilliantly illustrates the divide between legacy hardware and neuromorphic vision sensors. On one side, the global shutter captures a dense matrix of pixels at fixed intervals, wasting immense power. On the other, the neuromorphic approach treats every single pixel as an asynchronous independent agent. Each pixel only speaks when it perceives a logarithmic change in light intensity, completely eliminating the massive overhead of recording a stationary wall over and over again. The architecture for this biological mimicry has been quietly evolving for decades. In 1988, Caltech pioneers Carver Mead and Mishima Howell drafted the initial silicon retina blueprint. The early era saw initial dynamic vision sensors severely constrained by low resolution, but the latency of development has collapsed. Approaching the 2026 hardware tipping point, modern commercial integration achieves something extraordinary. It produces up to 1,000 times less data than a conventional camera, yet achieves a temporal resolution equivalent to 10,000 frames per second. This brings us to the 1 microsecond barrier.
The physical limitations of traditional optics are being shattered by an uncompromising performance gap. Conventional CMOS sensors struggle heavily, burdened by a latency of roughly 16 milliseconds at 60 frames per second. The event-based sensor reacts in less than 10 microseconds. We are looking at a temporal resolution of precisely 1 microsecond per event. At this scale, a machine can track a bullet in flight, or the rapid oscillation of a hummingbird's wing, with absolutely zero motion blur.
Because these asynchronous pixels respond to logarithmic changes, their dynamic range is explosive, reaching over 120 decibels. A standard camera is blinded by the extremes of a dark tunnel or a bright sun. A silicon retina sees both simultaneously, perfectly mirroring the natural, adaptable capability of the human eye.
But an eye is useless without the neuromorphic brain. An eye that sees in microseconds requires a mind that thinks in discrete events. Traditional deep learning architectures multiply continuous values in massive, power-hungry cycles. They are entirely unsuited for the sparse, asynchronous stream of a silicon retina. The absolute necessity here is spiking neural networks. In these architectures, neurons only fire when their membrane potential exceeds a threshold. It is a direct mimicry of biological neural dynamics, enabling a highly efficient 3D voxel grid encoding that tracks the evolution of events across both time and space.
When an event camera is physically paired with a neuromorphic processor such as Intel's Loihi 2 chip, the result is a unified eye-brain architecture. Operating on mere milliwatt-scale power, this synthesis achieves always-on autonomy. It is the exact breakthrough required to bring untethered awareness to wearable exoskeletons and microscopic robots operating in power-scarce environments.
The physical manifestation of this speed is found in the Goalie protocol.
The legendary robotic Goalie developed at ETH Zurich utilizes a dynamic vision sensor with the remarkably small array of just 128 by 128 pixels. Yet, it achieves an astonishing reaction time of exactly 3 milliseconds. This allows the machine to intercept physical projectiles shot from a distance of only 1 meter, maintaining nearly 100% accuracy. The crucial point is not just the speed, but the microscopic processing requirement.
The Goalie executes these high-speed interceptions with a peak CPU load of less than 4%. The immense power drain of traditional vision systems is entirely bypassed. To match the equivalent 550 Hz update rate using standard vision technology, a system would face a massive data burden. It would require processing 16 megabytes of raw pixel data every single second, monopolizing the resources of an entire computer just to see the ball. The event-based Goalie treats the incoming threat as a continuous stream of living information, entirely ignoring stationary background distractors. It tracks the physical threat precisely via its velocity vector and instantly plans an open-loop arm movement for interception. There is no stutter, there is no frame, only continuous, reactive flow. This technology is no longer confined to the lab, thanks to the stacked sensor revolution. The transition from isolated prototypes to global commercial reality relies on a critical manufacturing breakthrough. Driven by developers like Prophesee and Sony, engineers are utilizing QQ connection technology. They are successfully stacking the back-illuminated pixel chip directly onto the logic circuits. This achieves high-definition resolution at an industry-leading 4.86 micrometer scale, maintaining absolute microsecond precision without expanding the physical footprint. We are now crossing into the synthetic frontier. We are observing a profound philosophical evolution in the nature of machines. This is silicon organic synthesis. It is the permanent departure from the industrial snapshot mentality. By adopting the continuous vitality of biological perception, agile robotics are fundamentally transformed. This synthesis is the ultimate necessity for drones navigating dense forests at 50 kilometers per hour, and it is the absolute foundation for mission-critical autonomous defense systems, where a fraction of a millisecond determines success or catastrophic failure. The frame was a necessary illusion for the 20th century. But as machines awaken to a continuous, high-speed stream of reality, their perception will outpace our own. Is a 1 microsecond reaction time a safety feature or a future risk we aren't ready for?